All right, didn't get any emails other than just normal emails. So, again, these are just office hours. These are not pre scheduled lectures or recordings. So, if you have questions, you can ask them. I'm going to keep the camera on for about 5 more minutes, but not seeing any concurrent viewers and getting emails. I'm guessing not a lot of people show up today. Only comment I have for today is that keep in mind that we are now past the 60% mark. This is past the WWF date. So if you engage in the course, if you log into the discussion boards, if you, you took the exam, you're in the course now. So you're kind of committed there until the fall. Now the final is coming up in I think 4 weeks, something like that. It's coming up on the way. So actually, no, 3 weeks. So I will send out more information as we get closer and closer to the final exam. It is a 35 question multiple choice exam. You can submit work for partial credit. It needs to be taken in proctored unless you can give me a documentation as to why. And again, send me the documentation the week beforehand just so I can make sure, you know, everything's taken care of. It's easier to take care of it the week before of than it is the week up. But other than that, that's really all I've got to say. So again, I got the camera up for another 5 minutes. After that, if I don't really see any activity, I'm going to put up just a screen so you don't have to listen to me type on the keyboard. But yeah, if you got questions, feel free to ask them. Oh, hello. Alright, since I'm not seeing any questions being put up, I'm going to go ahead and just kind of switch the video off. Again, if you have questions, feel free to post them in the chat. Otherwise, I'm going to get some work done. All right, so just got a question about question 3 on the exam, but the questions are actually scrambled, so you're gonna have to give me a minute to actually look up that particular question. So on the exam, the first 10 multiple choices all come from different pools. Each question came from a pool of questions, and then within those 10 pools were scattered. So yeah, I need to go figure out which specific question was number 3. So it looks like on this one, what would happen if more HCl was added to the reaction? And unfortunately, it's not showing me what the other multiple choice questions were. So we have H2CO3 going back and forth to H plus HCO3 minus 1. And if we add HCl, oh, actually no, double dissolution, carbonate and H plus. So when we add HCl, we're adding this, and what it's going to do is it's going to drive the reverse reaction. So in this case, carbonic acid is this. So what we'd expect to see is more carbonic acid being formed, as Le Chatelier's principle says that if we add products, we're going to drive the reverse reaction. More carbonic acid would dissociate. So if that was the answer that was given, that would actually require the reaction to go forward. So I think you had the right idea. It's just kind of the wrong direction. You're going to add H plus, which is going to make more carbonic acid, not dissociate. Now, if you remove the H plus, if you got rid of that, you definitely drive the forward reaction. So if we add something like sodium hydroxide would pick off this H plus, and you would definitely make the carbonic acid dissolve more. So instead of forming, so it's just kind of, hold on, let me bring the question back up. So the question you got to ask, how would you know if it's dissociate? So to dissociate is to break in two, or dissociate is to fall apart. And then, so it couldn't be dissociate because it's not going to fall apart. Formed is just going to be kind of like make. When the homework problem showed an example of the reactant dissolving, but I still understand the difference when using this principle. Okay, so let's consider a few examples. An acid, a solid, what's another good one? And an actual reaction. So there are special cases for when we have one thing on one side. And my marker is starting to die. Just a minute. So if we have one thing on one side, there are a few ways we can describe how it goes from one thing to two things. So one term is decomposition. And this would have been a reaction that would have been taught in 151, or decomposition reactions, where there's one on one side and then it decomposes into things on the other. So we would not be wrong to say that these decompose as they go to one thing to two things, but then within decomposition there's special cases. So dissociation is the big key thing here. So association means to be around other people or associate with them. So dissociation is the opposite. When we dissociate, we no longer are with people. So when we say something dissociates, we mean it falls apart. The individual components fall apart. But the components originally made up one thing. We're just basically seeing, in this case, an acid, a conjugate base and its hydrogen ion fall apart. In this case, we see the calcium phosphide ions fall apart, but those individual components don't really change. They don't bond to anything else. So we can use dissociation for both of these, and typically you're going to see the dissociation term referring to acids. So acids dissociate. They fall apart into H plus and the conjugate base. Another term we can have is dissolution. So in terms of dissolution, what happens is that it goes into water. So to say something dissolution or anything, dissolution is another way of saying dissolve. There we go. So we can also say that this dissolves or dissolutes. And they're all kind of the same thing, meaning that we have a solid going into water. So in this case, we have a solid and it goes into an AQ. But we would never say that an acid dissolves or dissolutes because it's already got the AQ on it. And I realize, like, these are just kind of like little nuances in the words. I totally understand, like, it's just a new vocabulary. In terms of this, we would never use either one. So if we have more than one on both, if we have more than one on the left side, we would never say that this dissociate, the nitrogen and hydrogen dissociate, or they dissolve, or they dissolute. But because we have the ammonia on the one side, we could say that, well, even then we really wouldn't want to say that. And the reason we don't want to say that is up here things are just falling apart, but we can definitely see how they come back together. Here we're making and breaking bonds. And so when we're making and breaking bonds, this dissociate, dissolve, dissolutes, decomposition no longer really applies because we are both making and breaking bonds. So something is decomposing as well as forming a synthesis. And so if you have both decomposition and synthesis going on at the same time, so breaking bonds and making bonds, we would just say that it would drive the forward reverse reaction, but we don't really have verbiage to describe this. But the big thing is like what happens on the other side. So if we start with one thing and it becomes two things, are those two things the products of making and breaking bonds? Because if it isn't both making and breaking bonds, then we can say dissociates, dissolves, dissolutes, decomposes. Or if we go the other way, we can say that it forms, that it precipitates for the solid. Those would be the words that would show up in that case. The easy way to keep track of it, this DIS prefix, so if you see DE or DIS, this usually means comes apart. So if we want to describe one thing breaking into many things, you're typically going to see a DE or a DI or a DIS prefix at the start of the word, and that tells you it comes apart. And then as far as words for about when they come back together, it's kind of a tip off to English. We don't really talk about like things coming together so much as things falling apart. That's where you're going to see words. So if you see the reverse where something is being formed, you're not going to see DE or DIS in the word describing it. So I think conceptually you understand like shifting left or right for adding or subtracting products and reactants. It's just the verbiage that goes with it. And honestly, that's just more nuance. It's hard to teach all these words because there's so many of them. And I'm not trying to pass the buck here. Like there are just a lot of words people can use to describe this. Correct. So you would say that calcium sulfite, the CaSO3, is formed because. So we'll do big picture first. We have CaSO3, AQ goes back and forth to Ca plus 2, AQ and sulfite SO3 minus 2, and we're adding SO3 minus 2. So by Le Chatelier's principle, we're adding a product, which means we're going to drive the reverse reaction. So in this case, we would say that it would be formed because we're making it. So since we're making it by driving the reverse reaction, you would be correct to say it's formed. Whereas if we remove the bisulfite, so if we took the reverse, we said, oh, we're going to remove the bisulfite, or the sulfite, then we would say that the calcium sulfate dissolved, dissociated, decomposed. And again, you see this DIS-DE root coming back. You're welcome. Other questions out there? Yes, they do actually. So there is a big difference between Helmholtz and Gibbs. So delta G here is delta H minus T delta S. There are more terms that can appear. For the delta F, it's delta U minus T delta S. With the delta H here being delta U plus delta PV. And so here's the big implication here. And a lot of people didn't catch this when they did a discussion board. This is work. So the big difference between the Gibbs and the Helmholtz is how they can exchange energy between themselves and their environment. So every system can be broken into a system and the environment. So the environment is everything outside the system we're considering. And I'm going to erase this. If we have poor marker. I just need to throw this away, get rid of that temptation. Close enough. So let's say we have the Helmholtz system versus a Gibbs system. and they're both in an environment. So if we look at how the system can exchange energy here, if we're under constant volume, there's only one way for energy to get back and forth, and that's through heat. If we're under constant pressure, there's two ways. One is heat, and the second is that the system can change its volume, or it can have its volume changed. And in this case, we get work. And this has massive implications. So if we have a fixed volume system, first of all, we're making a very rigid statement about like what it's in. It's in a sealed container. Whereas our constant pressure system is actually open to the environment because the environment is maintaining that constant pressure. The second is that any energy exchange between the environment and the system for Helmholtz can only be heat. There's no other way to exchange energy. So if these two are at the same temperature, we're not going to really see energy exchange between the two. But if we go to the Gibbs system, so let's say these two temperatures are the same, even though these temperatures may be the same, if the system somehow loses moles of gas, so let's say you're running a reaction like you're capturing CO2 with calcium oxide to give you calcium carbonate. As the pressure goes down, the system will actually get smaller and smaller and smaller. And so what happens is the environment does work onto the system and actually gains energy. So let's say for both we're running this reaction, calcium oxide plus CO2. Goes to calcium carbonate. As the pressure drops here, so we have PV equals nRT, as the pressure begins to drop, our volume is constant and our moles are going down. So that's why we see the pressure drop, but we may not necessarily see a temperature change between these two. Whereas if we look at this system, as the pressure drops, the environment will compensate and will begin to push on it more and more and more. And so this ends up actually getting extra work done to it. It actually takes more energy is absorbed by this than would be absorbed in this case. So this is why we have to make that distinction. If a system can't do work or can't be worked on, it means that the only way for a system and environment to exchange energy is through heat. And as long as we don't have a temperature difference between the two, we shouldn't see any energy exchanged with the environment. Whereas in this case, even if you keep the reaction like completely at the same temperature, you have to compensate for work effects as well. So even though a temperature may not change because the pressure changes within the system, the environment does work on it or the system loses energy to work. So there's just a lot more in terms of how energy is exchanged. Now it is kind of nuanced. I will admit that for most of the world operates in Gibbs free energy. And that's because we typically keep everything open to the atmosphere. So particularly in a lab, we almost always work with Gibbs because we're open to the atmosphere, and the atmosphere is generally sitting at about 1 atmosphere of pressure. But if you do seal something inside a steel chamber, which happens with bomb calorimetry, you can get yourself into like making some bad approximations, particularly with heat capacities. That shows up a lot in this analysis. That because we're no longer compensating for the pressure, yeah, I know that's kind of a wandering tangent, but yeah, that's the big thing. Work is the very big thing there. Now, the properties of Gibbs and Helmholtz are very similar in the sense that a negative delta G means a reaction is spontaneous, a negative delta F means a reaction is spontaneous. But what factors into calculating the Gibbs energy and the Helmholtz energy is difference between the two. It's just that delta PV term, but it's still important. Hello. Yeah, you're welcome, Geneva. What questions do you have for me, Hardik? Other questions out there? Voice is low. I may need to crank up the volume on the receiver. There we go. That should be a little bit better. Microphone might be a little old on this webcam. Thanks for letting me know, though. All right, so I give it another minute. If people don't have questions, I'll just switch it back to the waiting screen. Do you have a little bit of paperwork I need to file today? All right, I'm just going to put the standby screen again. If you got questions, please feel free to ask them in the chat. I'm just getting some work done, so please feel free to interrupt. I just don't think you want to listen to me type on a laptop for a while. All right, not seeing any more questions. So again, these are office hours. These are not lectures. So if you have questions, you need to bring them and ask them. The Just chat bar is always open. So I will see y'all tomorrow. Thanks for those of you who showed up, especially those from India, and talk to you later.